Hello everybody, welcome to my channel. Today we will see about completely randomized design using the AgroR package. So in order to load this package, you can use an install.packages AgroR that released in the that released version from the CRAN, as well as alternatively you can use the from the GitHub, the development one. So you can use both of them. Then let's start our business. I already imported my data, and the data is composed of 6 different genotypes and 3 response variables. And my genotype is 6, as you will see here, 6 and 3 different response variables like GY stands for grain yield, straw yield, and here is pH is the plant height. So let's load. I already load or install the package, so no need to do that. Just call the package by using the library function. Then in order to use or in order to compute a completely randomized design in AgroR package, the function to compute CR design is DIC. And the full function here is you have to use function with, then immediately in the parentheses you have to specify your data. So in our case, my data name is D, and followed by comma, followed by the function that helps us to compute completely randomized design. Then DIC, then is followed by the first that should come here is genotype, or maybe it is a treatment for you. Then it's followed by the response variable. In our case, GY is my response variable, and which stands for grain yield. Then ylab here is y-axis title is grain yield in the form of ton per hectare, and the default for here is to compare the mean separation is the tukey. Again, also the advantage of this package is help us to compute homogeneity of variance, normality of the normality distribution, even independent of experimental error using the Durbin method. And again, there are a number of multiple comparisons like Scott-Knott, Duncan, least significance difference, and the tukey. So let's see the result. And before that, it's also display the bar plot along with superscript or the significance letter together with their mean value. Again, also it displays the p-value and the CV, or the coefficient of variation. So this helps us to minimize the error that most of statisticians, when computing the bar plot, they can fail to get the bar plot. So this will lessen this effect. So let's see. Yeah. Let's start from the result. As you can see here, the normality of errors is checked by the Shapiro or Wilkes. There are a number of around six way of checking the normality of errors, but the default one is Shapiro or Wilkes. So the p-value here is it's greater than 0.05. This means we can assume that error can be considered what is normal, so we never reject the null hypothesis. Then when it comes to homogeneity of variance, the default method is Bartlett test. Alternatively, you can use a levene test. Again, the p-value indicates that is non-significant. That means the p-value is greater than 0.05, and again we can consider there is homogeneity of variance among the groups. And again, also here is the Durbin Watson statistics for checking of independence from errors. So again, error can be considered as dependent since the p-value is 0.19, which is greater than 0.05. Again, there is some additional information. For example, here the coefficient of variation in percentage is 10.84. Again, the mean square to the ratio is 0.92. The mean is 2.2. The median is 2.25. Again, there is no significant outliers in our data, and again, it also gives you the analysis of the variance. Here is the treatment degree of freedom, since we have 6 treatments and we are expecting, yes, unit was expressed by numbers, so it's 5, and 10 square, mean square, F value, and their p values, which means they're statistically significant. So we may reject our null hypothesis, and we conclude that there is a difference among, at least 2 treatments are differ among the groups. So as I mentioned before, the mean comparison for such condition, the default method is a tukey honest significance difference, and on the basis of these, genotype 5, 4, 3, 6 are statistically similar to this group, and while genotype 3, 4, 5 as compared to genotype 1 and 2 are statistically differ, but the rest are the same as I mentioned before. So alternatively, you can get the bar plots along its p-value, along its coefficient of variation. Here is CV 10.84. Again, the p-value is less than 0.01, and here is the mean value for genotype 1, the mean value for genotype 2, and up to genotype 6. Along it is letters, yeah, the letters that help us to differentiate whether the treatment of one group is different from other groups. So for example, G1 and G2 share the same letters, so we consider that those genotypes are not statistically significant, but as compared to this one, it is differ because they didn't share any common letter. But all, starting from genotype 3, 4, and 5, they are statistically par or similar. And again, it's also similar with this one. Again, genotype 6 and genotype 2 and genotype 1 are statistically the same because they share B in a common way. So this is one of the advantages of the AgroR package to display the bar plot. So let's continue by adjusting or further modification. For example, I use this code and the default is a tukey, and the multiple comparison is tukey. The normality is a Shapiro or Wilkes. It's a default. But if you want to convert, for example, if you want to convert from the default of Shapiro Wilkes to other, you have to use you have different options like this one, Anderson, Kramer, Pearson, and Shapiro Francia. So you can select either of these or this on the basis of your interest. Again, if you want to compare whether is violated or not for homogeneity of balance, you can use a Bartlett test to the default method, but if you want to change into levene test or levene method, you have to use the function the code levene here instead of BT or Bartlett test. And there are 4 different multiple comparison tests. The first one is tukey. Tukey is a default method, and you can change tukey into a least significance difference or Duncan or Scott-Knott. So if you want to do with LSD, just type LSD. If you want to use a Duncan, just type in similar way. Again, type in this fashion. So if I want to change from the default or from tukey to multiple to the Scott-Knott, you have to add the function mcomp. Mcomp stands for multiple comparison, and ylab means it is the y axis. So all things are the same, but exceptional of what is the mean comparison. Yeah, if you compare the multiple comparison test, the tukey and the Scott-Knott, C is yes, somehow is differ from the previous one. Yeah. But the CV, all the things are the same, but the difference is what the multiple comparison. Even the bar plots are changed. Yeah. Furthermore, if I want to convert from SK to Duncan, just simply run all the codes, but with the exception of what this one. That means you have to include Duncan instead of SK. Yeah, yeah. Still, it is different. Here is BC, but in the case of SNK or Scott-Knott, only it is CC. Yeah, but all the remaining things are, or the remaining information are the same. So let's go to some modification. For example, you may want to change the appearance of this box plot. You may want to discard coefficient of variation, the p-value, and also if you want to discard the mean values. Again, if you want to give the bar plot size, and you can amend it upon your on the basis of your interest. So let's do with the function, then followed by data name, and followed by the functions that help us to compute a completely randomized design. And Gen is our treatment, which stands for genotype, grain yield. ylab means it is on the y-axis, then it's in the form of ton per hectare. And again, xlab is our treatment. So our treatment is the genotypes. So if I want to discard coefficient of variation from the bar plot, as you can see here is 10.84 is displayed. So if I want to remove this one, just say CV is equals to false. And again, if you want to remove the mean values on and only displaying the letters, so addmean is equals to false. And again, if you want to increase or decrease the size of text of both x-axis G1, G2, and also the grain yield, so you can again increase or decrease on the basis of your preference. And again, if you want to increase the label size means it is the letter or the superscript letter, that means A, C, B, C. If you want to increase this one, you have to use some level. Let's say 6. Yeah, let's say 6. And again, sometimes your treatment name may be large. Then if you want to display instead of this 0 angle, or if you want to some inclined angle, if you want to display into some inclined angle, you can adjust the angle to 45 degree. And again, if you want to change the size of the bar, that means this means the size of the bar means this one. So if you want to change the size of this bar, again you can adjust to any number that you want. And again, here is the sub means the distance of the superscript. For example, if you want to decrease the distance between this error bar, so you can adjust on the basis of your preference. So sub means it helps us to increase far away from the bar plot or to decrease the distance between or to approach to the bar, the error bar. So in order to do that, you have to use the sub one. And again, angle.label means again if you want uh, to change the level of A, B, C, D to something, that means here is straight, somehow it's 0 degree. So if you want to change 45 degree or 180 degree, so you have to use the angle.label equal to 0. And if we want to change the normality into SW means it is Shapiro-Wilkes, but to understand that link to Kramer, for example here, let's show you SF, CVM, AD. So if you want to convert to that one, so you have to use norm. Norm, which stands for normality. This one is a multiple comparison I already showed you. And if you want to change, here is homogeneity of variance from Bartlett test to levene test. So you have to use, instead of BT, you can use what? The levene. Yeah, here is levene instead of Bartlett test. If you are interested to use the levene, so this one. And again, fill. If you give different color for different genotypes, just type only trait here. Or if you want to convert into different in the same color, so you have to specify the color that you want. For example, it's maybe red, it's maybe pink, it's maybe violet, it's maybe blue. So you can do that. So type this and submit to our studio. So as you can see here, let's zoom in. Yeah, as you can see here, the color is changed totally to the number of which is called the number of genotypes, and again the bar size also is decreases, and the levels of superscript is also increases, and again the distance between the top of the error bar and the superscript also it's also decreased. So by this way you can adjust. For example, let's change this into a 45 degree, and the previous one the angle of the genotype or the treatment name is 0, but now it is somehow inclined. And again, if you remember, there is a p-value and a coefficient of variation, but we omitted the p-values as well as the CV value from our box plot. So let's, for example, if I want to change the angle.label, you are expecting to change from 0 degree to what? The BCC value A, this value into 45 degree. Let's show you. Yes, it's changed from 0 degree to 45 degree. And if I'm interested, for example, here is the addmean also discarded from our box plot. For example, if I say true, so mean value together with what their mean will be displayed here. So if you are interested in this way, you can do this one. Again, the size is a little bit big. So if I want to decrease this size, so go here, label.size, which is 6. Let's decrease to 4, and let's show you. Yes, now it is decreased, and let's change from what it is to 0 degree. Here is 45 degree. Let's change to 0 degree. In order to do that, you have to just angle.label to what? To 0. Yeah, yeah. Then let's discard the mean value. So in order to discard that one, simply do what? Into what? False. Addmean into false. Yeah, yeah. So the mean value is discarded from our plot. And again, let's put this BC value around to here. So in order to do that, you have to change what? Here is the sub. For example, let's do here 0.5, and let's see the picture. Yeah, it's far away from the what? From the error bar. And if you decrease the number of the sub, let's say here is 0.01. Yeah, yeah, it is even in it even come across on the error bar. And again, if you want to increase the size of this error bar, you can do with what? Width. You can do with what? Here is width of bar. Let's say 0.4. Yeah, let's change it into some way. So let's put this values up around 0.1. Let's see. Is that good? Yeah, it's good. And let's change the width of the error bar into 0.1. I think it's good. Yeah, somehow it's good. But you can adjust on the basis of your preference. Let's say 0.1. Yeah, it's good. But let's make 0.05. In any case, you can adjust your bar plots on the basis of your preference. And let's display CV into our bar plot. In order to do that, just type your CV is equals to what? CV is equals to true. Yeah, I'm expecting CV and the p-value will be displayed here. Yeah. Again, let's change this G1, G2 from inclined to 0 degree. In order to do that, go to what? The where is, yeah, angle. Angle. If you change this one, so the genotype will appear into this way. What's left? Let's make all the colors the same, and you can go here into, let's say, red. Yeah, so all the genotypes display represented by red color. Red color. Yes. So by this way, you can do a completely randomized design in AgroR Package. So if you have any question regarding to my tutorial, as usual, you can use YouTube comment box as well as my email, work.tasfan@gmail.com. See you soon.